Welcome to EDU World Space.
Hello. In this problem, we are dealing with two cars that are headed towards each other. So let's see what that looks like. We have something like this, where we have a road, then we have, let's say, car A, we'll label it mass M sub big A, and it's heading to the right at velocity v sub A. And we have another car. Sorry, my car drawings are not the best. That is mass M sub big B, and it is heading to the left at a velocity b here. Now, we're asked to find several things, and we're given a couple definitions for quantities in this problem. So I actually think it's easier to do part B first. And so what part B is we are looking for the amount of energy that is absorbed by these cars when they impact each other. And we're given a definition. We're saying that this energy's E sub A, the energy that car A absorbs in the impact, and energy E sub B, the energy that car B absorbs in the impact, is equal to basically its loss of kinetic energy with reference to a frame that is moving along with the center of mass of this system. So we actually have to find a few things and think of a concept or two before we go much further. So if we're going to want to put ourselves in a reference frame that's moving along with the center of mass of the system, we need to find, right, the velocity of the center of mass of the system. Well, we know how to find that. That's given by adding up the total momentum, I'll put capital P here, of our entire system and dividing it by the total mass of our entire system. We're going to consider both cars as our system, right? So let's add up the total momentum of the system. We know that should be constant both before and after the collision, so it doesn't matter which case we choose. So let's let's add up the total momentum of the system right now. So that would be in this case before the collision, so it's mass m sub a times velocity VA. And since, let's put ourselves in a coordinate system where to the right is considered something positive and to the left is considered something negative. So the momentum of the car A is to the right, so that's a positive momentum. Let me undo that there. A positive momentum here. And then the momentum from car B is headed to the left, so it's actually going to be negative. Mass of car B times velocity of car B, and then we divide it by our total mass of the system. Now, we're given several values for the problem. For the values in the problem, let's write these out now. The mass of car A, let me write that a little better here. The mass of car A is equal to, let's see, 1,600 kilograms. The mass of car B is equal to only 900 kilograms. The velocity of car A, well, it's to the right, and it is, let's see, 90 kilometers per hour. And velocity B is going to be 60 kilometers per hour. Okay, so if we take all these numbers and plug them into this equation, remembering to convert from kilometers per hour to meters per second, we end up seeing that the center of mass of this system heads, we get an answer of a positive 10 meters per second when I convert things to meters per second, and that means that the center of mass of the system is heading to the right at 10 meters per second, right? Okay. Now, if that's the case, that's a good number to know. We're going to need that for our calculations. And let's make a conceptual check here. If this is the case, right, so we're moving to the right here at 10 meters per second here. We're moving along with the velocity of the center of mass, right? Now, if we're moving in a system that's moving at the same speed as the center of mass, what's going to be the final state of our system once these two things collide, right? So after the two cars collide, right, they're going to be kind of crumpled up on the front here, something like this. This will be car A. It's just a little illustration here. And this is car B, right? It's not the best car in the world, but maybe the accident wasn't that great. So if we were already moving in a reference frame that was moving with the center of mass of the system, and now all of a sudden, all of a sudden, the two cars collide together in a perfectly plastic collision. I believe that's true. Yeah, it's perfectly plastic, which means that our cars are going to stick together. Well, the total momentum, right, of the system cannot change. So once these things collide, if we're already moving along with the velocity of the center of mass, then we should be moving in a system, or will be in a system, a reference frame, that is one in which the cars that collide together are now at rest. So if we're moving along in a system that's moving along with the same velocity as the center of mass of the system, if momentum is conserved in a collision and the collision is perfectly plastic, right, the two cars must stick together and then remain at rest. Now, if we were in a frame of reference that we were in a rest frame that's not moving along with the system, we would see these cars crash, right? And just through this calculation, this is the same thing, right, as the velocity of the two cars combined as viewed from a frame of reference, viewed from a rest frame, right? So if that's the case and these things is perfectly plastic, right, the cars from a rest frame, the two cars are going to be still moving at 10 meters a second to the right from our calculation. But if we're in a moving frame that is moving also at 10 meters a second to the right, then these two cars must be at rest in this moving frame. If that's the case, then the final kinetic energy in this moving frame is 0 joules, right? There's no kinetic energy because the cars are not moving. So when we calculate these E values, it's told to us that these values are given by definition to be the energy that is absorbed in a frame moving at the same rate as the center of mass of this system. So when I find these energies absorbed, right, so how much change in kinetic energy I have, say for car A, I already know what the final kinetic energy for car A was. We know that it must be 0 because in this frame, the cars are at rest. So we have no joules of energy afterward. Well, what energy did we have to begin with? So we subtract away this initial kinetic energy, which would have been 1/2 the mass of car A, times the velocity of car A. Well, this is in the rest frame, however, right? So by definition, we're in a moving frame that's moving at the same velocity at the center of mass. So we have to throw that in there, right? We plug in all of our values here that we'll have. Remember to convert VA into meters per second. Plug in 10 meters a second for the velocity of the center of mass. Plug in 1,600 kilograms for the mass of car A, and we end up getting a value of 180 kilojoules for how much energy is absorbed from the impact by car A. Now we do the same procedure for car B, right? It's going to, oops, I forgot to put my delta here. It's a change in energy. It's a change in the kinetic energy for car B. So that's going to be the difference in the final energy of car B minus the initial kinetic energy of car B. We know it must end with no kinetic energy because our two cars are at rest in this frame, and we take 1/2 mb times vb minus vcm squared. Now, remember, we're moving in a frame that's moving to the right at 10 meters a second. That means car B is actually going to be moving faster than that, right? So, and car B in this reference frame is moving to the left. This velocity is to the left, so we want to make sure to put our negative sign in there and we plug in. So it's actually going to be a negative 60 kilometers per second converted to meters per second into here, and minus 10 meters a second, right? So they're going to add up to be an even larger negative velocity because we're moving in a frame that's moving to the right. And then, of course, once we square it, the negatives go away. But we have to remember to put in that negative to make sure we're getting the right velocity for car B before the collision in a frame that's moving to the right. So put in all of our numbers that we know here, and we end up getting an answer of 320 kilojoules. Cool, so that's how much energy that each car absorbs in the collision. Now, I did part B first. Like I said, it was a little easier. Now let's do part A. So part A, we'll make a new slide here. Part A asks us to show that the ratio of the energies, right? So the energy absorbed by car A to the energy absorbed by car B in the collision is actually just equal to the ratio of the mass of car B to the mass of car A. It's basically saying that the energy absorbed is inversely proportional to the mass of the car. Right, so the larger the car is, the less energy it is going to absorb. Now, how do we show this? Well, we can do one of two ways, right? We could do it a little more complicated and have to handle and try to compare, right, our kinetic energy equations, right, and say that we try to compare these in some way. We have these from our previous slide here. It's our expressions, because this is actually 0 minus this number. So technically these are negative numbers, but those are going to cancel. So we can write our negatives here if we want. But another easier way to think about this is to remember, right, that we're working in a frame of reference that is moving along with the center of mass of our system. Now, when we do that, remember, at the end, right, what is the total momentum of the system in this reference frame? Well, it's 0, right? Both cars are not moving. That means that in this reference frame, that the total momentum before the collision must also be 0, right? So that means that in the reference frame that's moving at 10 meters a second to the right, the total momentum after the collision and before the collision must be 0. So that means the total positive momentum that car A has must be equal and opposite in sign to the momentum that car B has, right? Such that when they add together, they end up being 0. And so we're going to write that, right? That the total momentum, or the momentum of car A, ends up being negative the momentum of car B before the collision. Now, remember, the total kinetic energy that an object has can be expressed in terms of the momentum. So instead of doing 1/2 mv squared, we can do, well, I'll put the negative here because remember we're losing this energy. It's 1/2, right? It's over 2m, but the thing in the numerator is the momentum that the object possesses squared. So before the collision, right, this is the kinetic energy the object has before the collision, and this is the kinetic energy the car has before the collision in terms of the momentum it has before the collision. We can do the same thing down here for B. So we're going to lose the amount of energy absorbed by the car. Car B is the momentum it has before the collision divided by 2mb. Cool, right? So now what I can do is set up the ratio. This is a nice, little easier to work with than this one here, because of these nasty subtractions. So let's plug these equations into this ratio here. So we have the ratio of the energy absorbed by car A and the energy absorbed by car B is equal to, let's see, we'll do P, the negatives are going to cancel, so I'll just leave those out. PA squared, so the momentum car A has before collision, squared, divided by 2MA, all divided by the momentum car B has, squared, divided by 2MB. But remember, these two are equal and opposite to each other, but they're also squared. So what ends up happening is that PA squared, right, equals PB squared. So these two are equal, they cancel. The 2's are equal as well, and we have a 1 over MA in the numerator divided by a 1 over MB in the denominator. Let me rewrite that, MB in the denominator, which means we have MB over MA. And we have proven by looking at the conservation of momentum and the values of momentum that we have in this moving reference frame, that we actually can express the ratio of the energies absorbed by each car in the collision is just the ratio of the masses of the objects that are colliding in that collision. And there you go. That's how you solve that problem.